There we go. All right. So just like with all of our other meetings, I'll be recording me going over the notes for today. And then as soon as that is done and uploaded, I'll pop it in right here. And so today's Monday the 15th, or Tuesday, excuse me, 15th. So I'll pop it in on the Zoom meeting recording section of our classroom right under the atomic structure, because that's the name of the notes for today. And also, just as a reminder, I had some people in my other classes who were still a little bit kind of unsure of themselves in terms of the Google Classroom and finding old notes and stuff like that. So if you ever want to go find an old pair of notes, you just scroll down through the Google Classroom, and I have it organized into weeks. And then each note goes by the day that those notes were posted. And so like today is, like I mentioned, Tuesday the 15th. And so we're going to be learning about atomic structure today. So if you ever want to go back and look at these notes and maybe use them when you're going through the assignments for today and tomorrow, it's going to be right here, 9:15 Tuesday notes, atomic structure. And it's the exact same Google slides that I'm going through today are what is posted underneath those notes. So that's where you can go and find it if you ever want to go back and look at the notes over again. All righty, let's get things going. So I mentioned today we're talking about atoms, atomic structure, and the periodic table, which is like a big chart that tells us all about atoms. So atoms, like we'll talk about in a second, are the teeny tiny little most smallest particles that make up everything in not just the world, but the universe around us. Every single thing that exists is made up of atoms, whether it's air or water or you or me, your dog, the table, the computer, the stars up in the sky. It's all made out of atoms. And so today we're going to be talking a little bit about how these atoms are built. If atoms are the building blocks for everything else, what are the building blocks of atoms? What are these little particles that are all bunched together or zooming around here? That's the kind of stuff that we're going to be talking about today. So this is what is called the periodic table. So you may have seen this if you remember, like way back in your old like high school or middle school. The science room probably had one of these taped up on the walls somewhere. It's this big, huge, confusing looking chart with all of these different symbols and numbers and boxes and stuff all through it. And so a little bit later on in this week, we're going to talk in more detail about how the periodic table is structured and set up. But the main thing that I want you guys to know about it for right now is that every single one of these boxes on the periodic table is a different atom, a different element. So far, scientists have been able to discover 112 different individual atoms that combine with each other to make up everything else in the universe. So like, for example, you know that water is H2O. That's the chemical symbol of water. So we have two H or hydrogen atoms and one O or oxygen atom that go into building water. So each one of these boxes represents a different element or a different atom. So like I mentioned, we have hydrogen and oxygen. We have ones that you guys might have heard of before, like aluminum is this guy right here. Sodium or potassium, these two guys right here. Na is sodium and K is potassium. We've got things like neon over here, so like the stuff that goes into the neon lights of like a business. Helium, the stuff that you fill up like a party balloon with. All of those are different atoms, and they all have their own separate individual little box on the periodic table. So later on this week on Thursday, we'll talk about like how the periodic table is structured and why some of them are metals and some of them are non-metals, and the kind of ones in this zigzag in between section are metalloids. we'll talk about some of the stuff, what that means on Thursday. But for today, we're mostly just going to be focusing on these little boxes. What kind of information about an element or an atom can we get by looking at its little periodic table box? So, atoms. Like I mentioned, they are the smallest unit of matter. So they are kind of like the smallest little building blocks that go into building everything else in the universe. So like trees, air, dirt, water, stars, other planets, you, your cat, it's all built out of atoms. And they're super duper, incredibly teeny tiny small. Even the most powerful microscopes that scientists have ever created struggle to make a picture of a single atom. They're that super incredibly tiny. And so atoms have kind of the two different sections to them that we're about to talk about. They have kind of this middle section all clumped together in here, and this outer area with these little particles zooming around out here. And we'll talk more about what those are in just a second. But atoms themselves are made out of three different things. So a combination of three tiny, what are called subatomic particles, so super even tinier than atoms particles, called protons, neutrons, and electrons. And those three are what we're going to be spending most of today in these notes talking about, is what are they and how can we figure out how many go into building our atoms. So we have this middle section with some stuff zooming around the outside. This middle section has its own specific name, and it's called the nucleus. So the center of our atom is the nucleus. So this middle section with these particles all clumped really close together, that's the nucleus. So pretty much all of an atom's mass or weight, so mass is a scientific measurement involving weight. So like 99.999% of the weight of an atom comes from this nucleus right in here. And two of those three particles that we just talked about, the protons and the neutrons, are found in the nucleus. So we've got all bunched up, squished together in the nucleus. We've got two of our three different subatomic particles, teeny, teeny, tiny particles. Protons and neutrons go together in here, and that's what makes up the nucleus, like this center mass of the atom. So let's talk about these one by one, protons, neutrons, and electrons. So protons, like I just mentioned, are part of the nucleus. They go in that center section. And this little picture right here, they're colored in red so that you can tell the difference between some of the other ones. In reality, protons aren't a color. They're literally not big enough to produce a color if you're able to look at them. But in this case, they're colored in red so that you can differentiate between some of this other stuff. And the main thing to remember about protons for now is that they have a positive charge or a plus charge. So this one, pretty easy to remember. Protons have a positive charge. So P goes with P. Protons, positive. So this is one section of our nucleus, one part of the cluster of these tiny particles inside of the nucleus of an atom. So in our little picture, we've got some positive red protons hanging out here in our nucleus. Protons are positive. And that's going to be important a little later on. So make sure you stick that in your brain. So in our nucleus, we've got our protons that are positive. We also have our neutrons. So in this picture, the neutrons are what are colored in blue right down here. So they are also in the nucleus. So the protons and the neutrons put them together, and that's what makes up your nucleus, is those two guys clumped together, hanging out in kind of the middle of the atom. So neutrons have like a neutral charge. So essentially they have a charge of 0. So protons are positive, they get a plus. Neutrons are neutral, no charge. So people get tripped up with this all the time because they think that if the protons are the positives, then the neutrons have to be the negatives. And that's not true. That's bad. Don't think like that. You're too smart for that. Neutrons, instead, have the neutral charge. So that's how I remember it, is based on the first couple letters here. The neutrons are neutral. Or you could also think of it as neutrons have no charge, 0 charge. So we've got some positives and some neutrals hanging out in our nucleus, all bunched up together. So the cool thing about neutrons is that if you take the protons and the neutrons together, that pretty much tells you the mass or the atomic weight of the atom. So we'll talk a lot more about mass in a couple slides, but just keep in mind for right now that the mass of an atom, you can figure it out by doing the protons plus the neutrons. So if you know how many protons an atom has, and you know how many neutrons an atom has, if you add those together, you'll be able to figure out the weight or the mass of the atom. So neutrons hang out in the nucleus along with the protons. They are neutrally charged, so they have no charge, 0 charge. And they get added to the protons in order to tell us how heavy this atom is compared to other atoms. So the more protons and neutrons that you've got in your nucleus, the heavier your atom will be. So that's 2 of our particles, protons and neutrons. But if you remember from a couple seconds ago, we also have a third one, and that one is our electrons. So the electrons do not go in the nucleus. Instead, they hang around outside of it. They kind of zoom around on the outside of the nucleus. We'll talk on Thursday. We'll talk on Thursday about the specific way that electrons orbit the nucleus, but we're not going to worry about that for right now. That's a later thing. But just know that they are not part of this center group, this center mass here. They are zooming around over the outside. So electrons, these are the guys that have the negative charge. So electrons are negative. They have a minus charge. So protons are positive. Neutrons have no charge. And then the electrons are our negative charges. So the way I like to kind of remember it for these guys is that electrons is where we get the word electricity from. And so if you get hit with electricity, that's bad for you, right? That's not going to be very fun. That's a negative experience. So electrons are negative. They carry negative charges, and they're what's responsible for electricity, which if it hits you, you're going to have a bad time. The other thing about electrons is that even compared to these super teeny tiny particles like the protons and the neutrons, they are even more teenier and tinier. So they're like 1/1000th the size and weight of these protons and neutrons. So they're so small, we don't even count them in the weight of the atom, right? So I've had people ask me before, like, Mr. Stanley, we have protons, neutrons, electrons. Don't we have to put them all together to figure out how heavy an atom is? And the answer is no, essentially. If you do like super precise electronical readings of the atoms, then maybe they do factor in and you get some very precise numbers. But for what we're going to do in this class, electrons are too small to be counted for the mass. They're too tiny and light. They're like if you stepped on a scale and you carried like a couple feathers and put those on there with you, that's not really going to alter the scale at all, right? They're too small to be picked up by the scale. So we don't, no matter how many electrons an atom might have, they don't get counted in to the overall weight. It's just the protons and the neutrons down here in the center. All right, so before we move on, any questions so far about our different types of particles that we've got in our atoms? So our protons, neutrons, electrons, anything that you're unsure about, want me to go over really quick, have a question about, anything like that so far?
Mr. Stanley, so you said neutrons have no charge, right?
Right.
Okay, I'm just trying to make sure. Thank you.
No problem. So yeah, so protons, positive, electrons, negative, and then neutrons are neutral, no charge. So if like a lot of times you'll see protons labeled with like a little plus sign, and you'll see electrons labeled with like a little minus sign. Neutrons get labeled with like a 0. They don't have a charge, so they don't count towards the overall charge of the atom. Exactly. Good question. All right, it looks like nothing is coming up in the chat either. So we'll move on to our next section, which is, now that we know a little bit about what these different particles are, the next thing that scientists want to know is how many of them are there? How can we figure out how many protons, neutrons, and electrons are in an atom? Well, luckily, it's really easy to figure out once you know kind of the tips and tricks. Specifically, the tips and tricks for knowing how to read the periodic table. So if you remember the very beginning of these notes, I showed you that huge table with all those little boxes with all the symbols and stuff in it called the periodic table. And so the table, each one of those boxes actually has enough information on it on a full-size table so that we can figure out information about the protons, neutrons, and electrons that an atom might have. So if you look at a single box of an element on the periodic table, they're all set up the exact same way. On a full-size table, they have 4 different pieces of information on them. So you may have noticed on the periodic table that I looked at the very beginning, it only has 2. It has our number and a little symbol, a little set of letters, because this periodic table is kind of really squished down in order to fit on this one slide to show you guys. But a full-size periodic table would have 4 things in each box. We've got the name of the atom. So in this case, we're looking at the atom Krypton. So other atoms that you may know are things like oxygen, neon, calcium, phosphorus, aluminum, gold, silver. All those are atoms, and so on their box they'll have their name written out. They'll also, in bigger letters, have a chemical symbol. So for most elements, their symbol is just the first 1 or 2 letters of that element. So some of the smaller letters just get 1 symbol. So like hydrogen, H is its symbol. Carbon is a C. Oxygen is an O. But the most of the atoms on the periodic table, they get a 2-letter symbol. So krypton is Kr. Calcium is Ca. Aluminum is Al. Zinc is Zi. There are some symbols that seem like they're kind of weird for the atom that they go with. So for example, gold has a chemical symbol of Ag, and silver is, I believe, Au. Potassium is K, and usually that has to do with what the original name of the element was in Latin. So the word for gold is different in Latin than it is in English. And so when scientists were first making the table, they gave the symbol to whatever the Latin name was. So those are the two kind of most straightforward pieces of information: name, symbol. So besides those two sets of words or letters, we also have two numbers on each box. The top number is called our atomic number, and that's kind of like the identifying number for each element. So every single element has a different atomic number, and they're labeled from 1 to 112. The bottom number, which is always going to be larger than the top number, is the atomic mass, or also sometimes called the atomic weight. So if you remember earlier when we said if you take the protons and neutrons and add them together, you'll get your atomic weight. That's what this number is referring to. Usually on like a full-size scientific periodic table, it'll be something with a decimal because they took super precise measurements of these different weights. And we'll talk about kind of how we deal with that in a little bit. But main things to know for right now is the smaller number up top is the atomic number, and the bigger number down on the bottom is the atomic mass, or the atomic weight. So for each element, each box of the periodic table has these 4 pieces of information in it, usually in this same order. The number up top, followed by the symbol in big letters, then the name in smaller letters, and then the atomic mass on the bottom. So the first thing that we're going to talk about, the name and the symbol are pretty straightforward, so we don't really have to talk about those anymore. But the first number I want to go over is the atomic number. So not only does each element have a different kind of unique identifying atomic number, that number is based on the number of protons in the nucleus of that atom. So however many protons that an atom has, scientists said, all right, we'll just stick that number on as the atomic number. So in this case, Krypton has an atomic number of 36, which means that it's got 36 protons in it. Every single atom of Krypton has 36 protons in the nucleus. So that's all that this number refers to. Essentially, when scientists were first putting together the periodic table, they're like, how do we order these atoms? How do we put them in order? What kind of order should we do? And to make it simple, they just decided proton number, that's going to be your atomic number. So every single element has a different number of protons. And that's the main way that scientists tell them apart from one element to another, is how many protons are in that nucleus. So you want to know for each element how many protons they got. Just look at that number up top. Depending on which table you're looking at, maybe it'll be in the top left, maybe it'll be in the top right, maybe it'll be front and center, right in the middle, but it almost always will be somewhere on the top of that box. So protons, atomic number, same thing. So our next number is our atomic weight, our atomic mass, down here at the bottom of the box. So our atomic weight tells us approximately how much does each atom weigh. And like I mentioned before, it takes into account how many protons and how many neutrons that there are. So when we're weighing atoms, atoms are so super duper incredibly small. Like if you took a pen and made a dot on a piece of paper, approximately 1 million atoms could fit across the span of that dot. That's how small they are. And so this atomic weight down here is obviously not referring to their weight in like ounces or grams or pounds or anything like that. Instead, scientists essentially came up with their own way of measuring atoms called AMUs, which stands for atomic mass units. And essentially what they did is said, all right, protons and neutrons, the bigger guys, they each equal 1 AMU. So when we stick the protons and neutrons together, that'll give us the total AMUs for the atom. And AMUs, as you might imagine, are incredibly small. Like I think 1 AMU is approximately like 1/millionth of 1 gram. Actually, probably even smaller, to be honest. It might be like 1/10,000,000th of a single gram. And so incredibly small weight, but that way they don't have to make these be like super tiny decimal numbers. They can just make them look like normal whole numbers, essentially. So that's what the number down on the bottom is, our atomic mass and weight. And so, like we mentioned before, we get that atomic weight by adding the protons and neutrons together, right? The electrons, we don't count them because they're too small, too little. So protons and neutrons combined make the atomic mass. What this means is that since we know the proton number, thanks to this atomic number guy right up here, and since we know the atomic mass, this bigger number down here at the bottom, we can use this to figure out not only how many protons, but also how many neutrons are in one atom of a particular element. And let's break down how that works. So we know how many protons we got. That's our atomic number. It says it right there on the box for us. Very kind. And we know that our atomic weight down there on the bottom is the protons and the neutrons added together. So if we take the number of protons out of the atomic weight, we'll just be left with how many neutrons are left, right? If the protons and neutrons together give us our atomic weight, then if we take the protons away from that weight, we can figure out how many neutrons are in our atom. So if we do the atomic weight minus our atomic number, which again is what tells us the protons, that gives us how many neutrons are in one atom. So let's look back at Krypton as an example. So we have Krypton right here. And I mentioned earlier that you'll notice a lot of times on the atomic weights that you'll see on a full-size scientific periodic table, they'll be listed as a decimal. In this class, whenever you see an atomic weight, I want you to round that to the closest whole number, the closest non-decimal number. So for Krypton, since that has a weight of 83.8, that's pretty close to 84. So we can just round it and call it an even 84. If the weight was a little bit smaller, so if it was like 83.3, 83.3 is pretty close to 83. So we just round that down and say, we'll just say it's an even 83, right? So you basically just round up or down to the closest whole number. In this case, Krypton, we can say that it has a weight of 84. So we've got our atomic number right here. That tells us that there are 36 protons in one atom of Krypton. Now we want to figure out the neutrons. So we know that our mass, when we round that 83.8 up, it becomes 84. So we'll just say 84 is the mass of Krypton. And we do mass minus the atomic number. So it mass minus the protons. And we just said that 36 is our proton number. So the atom Krypton has 36 protons and 48 neutrons in each atom, in each nucleus. So we did 84 as the weight minus 36 as the number of protons, and we got 48 neutrons out of that. So to find the neutrons, basically you just look at one of these boxes, you take the big number down on the bottom, you do that minus the smaller number up at the top, and that'll give you how many neutrons are in one atom. I know that process is obviously a little bit trickier than figuring out how many protons you got. So any questions about calculating neutrons, figuring out how many neutrons are in each atom of a particular element? Any questions on that calculation so far?
So basically, since the electrons don't count, we're mainly adding just the neutrons. I mean, not adding, subtracting the neutrons from the protons. I mean, the protons from the neutrons, correct? And then that would give us the answer like for a homework you gave us.
Close. So you're not subtracting the protons from the neutrons. You're subtracting them from the mass.
The mass, yes, that's what I don't know why I said that.
I know, it's tricky
the
to
mass
keep up
number. So the mass from the protons will give us what our neutrons are, correct?
Mm-hmm. Mass minus protons gives you the neutrons. Exactly. Exactly. All right, so speaking of electrons, like you mentioned, they don't really have any factor in this weight mass business at all, right? They're too tiny, itty bitty to deal with that. But a lot of times we still want to know how many neutrons or how many electrons, excuse me, are in an atom. So we've calculated protons and neutrons. How can we then go about figuring out electrons? Turns out, at least for our purposes, it's super simple. So the atoms that we're going to be looking at in this class are what are called neutral atoms, meaning that they have equal numbers of protons and electrons. So we mentioned that protons have a positive charge and electrons have a negative charge. So in neutral atoms, the stuff that we're going to be dealing with, we want atoms with no charge. We want them to be completely evenly balanced on their positive charges and their negative charges. We want those to be equal to each other. So neutral atoms have same number of protons and electrons. So however many protons that your atom has, that's how many electrons that it has. We want those positives and those negatives to be completely equal, completely balanced in order to have our nice neutral atom. So for the stuff that you're going to be working on, you want to balance those numbers. You want to make sure that you have the same number of protons and electrons in your atoms. A little bit like if we kept going if you took like a chemistry class later on in life, there are atoms that have more protons than electrons. They have more positives than negatives. So they'd have an overall positive charge. There are some atoms that naturally like to have more electrons than protons. So some atoms have an overall negative charge because there's more negatives than positives. But we're not really going to deal with that in this class, at least for the next week or two. And so we're going to be considering neutral atoms, which are balanced, totally equal protons and electrons. So the simplest example of this is our buddy hydrogen, the H in H2O. Hydrogen is the smallest and simplest atom that exists. Hydrogen has an atomic number of 1. It's the very first atom on the periodic table. So since it has a number of 1, it's got 1 proton in its nucleus. And since it has a proton in its nucleus, it has to have an electron, one single electron, orbiting around the outside. So again, balancing our protons and electrons, the same number of positive protons and the same number of negative electrons. Excuse me. Yeah. So on your, like when we're looking at the homework in a little bit and it's asking about figuring out numbers of protons, neutrons, and electrons, we want to make sure that we have the same number of protons and electrons in our every single one of the atoms that we're going to be looking at. All right, so let's look at a little bit more complex example than just hydrogen, because he's pretty simple and basic. Let's look at carbon instead. Carbon is a little bit more complex. He has an atomic number of 6, so a little bit more than hydrogen, who has just the 1. So here is carbon's periodic table box. And like I said, we've got our 4 different pieces of information in here. We've got our name written out, carbon, down here. We have the symbol. Carbon's one of the smaller atoms, so he just is lucky enough to get just a single letter C for his symbol. Carbon has an atomic number of 6 and a scientific atomic weight of 12.01, which we can essentially just say is 12. It's close enough to being 12. We'll just round this number to an even 12. So, how many electrons are in one atom of carbon? This is not a rhetorical question. Feel free to answer in the chat or unmute yourself. How many electrons does carbon have?
I have a question about the electrons. I'm trying to figure out if they are the exact same or if they are negative to make it like complete from the positive.
So electrons, when we talk about the number of them, we don't put a negative on their number. We just say, here is how many of them that there are.
So they would be the same as a proton? It would be 6?
Yep, exactly. And how did you figure out that carbon has 6 protons and electrons?
Because I looked at the atomic number, which makes
Bingo. Exactly. So our atomic number up here is 6. So that means that we have 6 protons, because again, if you notice the hint down here on the bottom, atomic number is equal to how many protons we got. And then, since we know that we have 6 protons, that means that we have to have 6 electrons as well. And to your question, Stacy, we don't have to say that there's like -6 electrons or anything like that. We know that they're negative. We can just say that there are 6 of them. Like if you counted the electrons, you'd be able to go 1, 2, 3, 4, 5, 6. So exactly, atomic number is 6, which means protons are 6, which means electrons are 6. All right, so throwing a little loop in here for you guys. How many neutrons could we find in one atom of carbon?
Six.
Stacy, 6 is exactly correct. And how did you figure out that carbon has 6 neutrons?
12 minus 6 equals 6.
Perfect. So neutrons, again, is weight. which is, like we said, 12 in this case, minus 6 up here at the top. So 12 of the weight minus 6 for the number and the protons gives us 6 neutrons. So sometimes the neutrons will also balance with the protons. That happens a lot with the smaller elements. But in general, as you get bigger and bigger elements, you start to get more and more neutrons. So like carbon is atomic number 6. He's pretty small. But something like Krypton with atomic number 36 is a lot bigger, and he has 48 neutrons. So his are not the exact same like we saw earlier. But Stacy is exactly right. You just do 12 minus 6, and that gets you 6 neutrons. All righty. Hey, Miss Penny, welcome in. So that is kind of the main gist of stuff that I wanted to hit with you guys for the electron, proton, neutron notes today, is how to figure out how many of those different particles that we have for each element. So does anybody have any question about any of the stuff we've gone over so far? The numbers, the weights, the protons, the electrons, the neutrons, anything like that?
I had a question about like the work.
Mm-hmm. Oh, Alicia, I think you got muted again.
But it's 18.998, correct? And
I think you muted yourself there accidentally for a little bit.
oh, sorry.
You're asking about like
No,
how you do the rounding.
But yes, the calculating the rounding. So what I said was like 18.998. We're gonna round it out to 19, right?
Perfect.
And then we're gonna do 19 minus 9, and that would give us the number for the electrons that all of them together that you're asking for.
Mm-hmm. Exactly.
Okay.
So if it's
Just trying to
so yeah, so on your homework, actually that brings up a good point. Let's go look at that really quick. All right, so the assignment that goes along with these notes is all about figuring out numbers of protons, neutrons, and electrons. And so if you fill out the Google Doc, it'll look something like this, where we have 6 different elements and their information from their little periodic table box. And so for each one of these elements, you would have to calculate the number of protons, the number of neutrons, and the number of electrons that are in one atom of fluorine, for example, or one atom of uranium. And then just like Alicia was asking, all of these are presented with their scientifically recorded atomic masses down here on the bottom. So you're going to see a lot of decimal points. But like I said earlier, we're just going to round those to the closest whole number. So like fluorine, 18.998. Like Alicia said, we'll just round that directly to 19. Radon, 222.018. You can just round that down to 222. And then most of these should be pretty straightforward. Borium is already rounded off for you. Some of the really big guys haven't been able to get super precisely measured yet. So scandium, you'd round up to 45. Uranium, you'd round down to 238, and same for platinum. So this is what it looks like on the Google Docs. If you do it through the Google form, which I know a lot of you guys like to use, it works a little bit differently, but it's still the exact same questions. It's just that for each atom, the Google form doesn't really allow me an easy way to list out protons, neutrons, and electrons all separately. So instead, I just want to make sure that you guys put all of that information into one answer. So for example, this is not the right answer. Do not write this in on your homework. But if you thought the answer for all three of those elements for fluorine was 5, then you would type in like 5 protons, 5 neutrons, 5 electrons. And so if you want to do the Google form version, the one that looks like this, all you have to do is physically write out how many and which particle you're talking about for each one of these elements. They're all the same elements. They all have the same information in them. But this way I didn't have to make like 3 separate questions for every single one of the little pictures of these boxes. And I think if you look at the classwork on the Google Classroom, it'll say something along the same. Yeah, if you do answer the Google form, make sure you list out all the particles in each answer. So each answer should have the protons, neutrons, and electrons listed. Or if you want to do the Google Doc, it's already listed out for you. You just have to put in whatever number you think fits best for each one of those 3 right in there.
So I had a question on the last number 6. Why is that one like? Why is it 264?
All right, you may have to say that one more time. You cut out a little bit in the middle there.
Oh, okay. On number 6, why is it that the 264 is it has that like parenthesis looking things around it, like
So
dots around it? Why? This,
good question. That essentially means that scientists haven't been able to measure borium, the mass of it, as precisely as like these other guys. And so the reason uranium is 238.029 is because they were able to use super precise technical instruments and make that very, very, very tiny measurement. For borium, I think it's a little bit more unstable, so they're not able to measure it quite as directly. And so essentially that's them saying this is the estimated mass. This is as close as we've been able to so far, but it's not as perfect, it's not as precise as these other guys that have all these decimal points on them.
Okay, thank you.
No problem. Good question. Anybody else have any questions on the homework, the assignment that is scheduled for today? So hopefully should be pretty straightforward, especially you can always go back and look at the notes for today if you need a little bit of a refresher. And remember that once we finish up with our conversation here, I'll put the recording of this meeting in our little Zoom meeting recording section up here at the top if you want to go back and watch a video of it later on. So tomorrow, obviously, we do not have a Zoom meeting, which means that you do have to complete an assignment in order to get attendance credit for tomorrow. And so tomorrow's assignment, I'll go ahead and give you a little bit of a sneak peek. It's actually a little bit simpler than the one even that's today. It's essentially just kind of a review of some of the basic concepts that we talked about in this class. And so it talks a little bit more about protons, neutrons, and electrons. And you use a little periodic table box to answer some basic questions about helium, and then to do some more very simple kind of calculations of protons and neutrons. Oh, and electrons. Also, can't forget about those guys. So again, since we don't have a Zoom meeting tomorrow, make sure that you either complete this worksheet, or if there's an old worksheet that you haven't gotten to yet, you can complete that one as well. As long as you complete something and turn it in to me, you'll be able to get your attendance credit for Wednesday, and then hopefully be able to come back and join us again on Zoom next Thursday. All right, any final questions about the notes from today, the homework that got posted for today, or the assignment that's coming up tomorrow? Any more element, atom, proton, neutron, electron questions? All righty, awesome. In that case, I'll go ahead and